Hello everyone, I'm Niharika Arora, a robotics engineer at Fetch Robotics, and today I'll be presenting our work on robot calibration. So we've created an open source calibration framework that I worked on as an intern at Fetch, and we use that to calibrate our robots. So we produce a lot of robots at Fetch, and we don't want to be spending too much time calibrating these robots. So fast and robust calibration system was needed to calibrate these robots and to create a great robot army. So first, I'll give a brief introduction to robot calibration. Then we'll go over the common calibration systems, namely camera calibration and robot calibration. Finally, I will talk about our two main calibration packages, Fetch calibration and robot calibration in detail. So robot calibration is an essential prerequisite to many mobile manipulation tasks, and for many mobile manipulation tasks to be successfully performed, the sensors and the kinematic chain of a robot must be very well aligned. So robot calibration is the process of determining the actual values of the kinematic parameters of an industrial robot. So these kinematic parameters are the joints and links of the robot. Take a surgical robot, for example. You need high precision and accuracy because you want to be able to operate upon the correct tissue or organ. So you need a very well calibrated robot. Or if your robot's manufacturing something, you want the robot to be very well calibrated because you want it to produce the exact thing you need. At Fetch, we need our Fetch robot to pick up objects on the shelves, and we don't want the arm to hit stuff to hit stuff around itself. So we need to know the exact model of the robot so that tasks like picking can be performed correctly. All right, so when people think about calibrating robots, they usually confuse it with camera calibration. And camera calibration is important because it lets you reconstruct a true world model. It lets you get a highly accurate representation of the real world from the captured images. But lenses aren't perfect, and camera calibration is important. The two different types of camera calibration, intrinsic calibration and extrinsic calibration. So intrinsic calibration is the process of estimating the internal parameters or the intrinsic parameters of the camera, like focal length, optical center, and distortion parameters. These are typically estimated using a least square estimate using measurements from a calibration pattern, typically like a checkerboard. Extrinsic calibration is the process of determining the extrinsic parameters like rotation and translation of the camera in the real world. So extrinsic calibration finds or calibrates the rigid transformation from the 3D world coordinate system to the 3D camera coordinate system, while the intrinsic calibration calibrates the projective transformation from the 3D camera coordinates into the 2D image coordinates. Okay, but robot calibration is much more than this. It's the calibration of the sensors and the kinematic chain of a robot, which consists of joints and links. So which for a robot basically means calibrating the camera and the kinematic chain together. So each joint is a potential source of error in the kinematic chain. So we need to make sure that each joint is calibrated properly and the sensor gives us accurate information. A number of systems exist for calibration of mobile manipulators, and several of them have open source implementations available. For example, the PR2 calibration package and the ROS industrial calibration, which was presented by Chris Lewis at ROSCon 2014. But these systems face a few challenges like an inability to generalize across sensors and platforms. So many of these systems are heavily designed or tuned around a particular set of sensors and are unable to generalize beyond those sensors. Slow calibration times. The calibration system built for the PR2 robot often took as much as 45 minutes for calibration to happen, with half of the time spent in actually capturing calibration data, while the other half spent in doing the actual optimization. Lack of robustness. So frequently, these calibration systems have issues which causes them to not get a good calibration on each and every attempt, which can be particularly detrimental, especially when your calibration takes a significant amount of time to redo. All right, so before I start discussing about a calibration system, let me quickly go over our Fetch robot and explain what we're trying to calibrate here. So Fetch is a mobile manipulator, which consists of a differential drive robot base, and it has a 7-degree of freedom arm, a pan, tilt, and tilt joint, and also a torsal lift actuator. It has a PrimeSense 3D Carmine sensor installed in its head. So our aim was to calibrate each and every joint in the arm, the head tilt and head pan joints, and the head camera parameters simultaneously. Okay, so we wanted to automate this calibration process and make it fast and reliable. So we have robots both in the field and in academia, and neither warehouse operators nor researchers want a badly calibrated robot or want to spend too much time calibrating their robot. So Fetch calibration is a hand-eye calibration system, and what this means is that we have our calibration targets in our gripper frame, which is the end effector frame, and we're trying to estimate the transform or the relationship between each joint that exists between the sensor, that is the camera, and the end effector frame or the gripper frame. So it's essentially making the robots more human-like, or giving the robot hand-eye coordination just like we humans subconsciously have. So if you look at the two images, these images show the robot model in ROS. So the image on the left shows an uncalibrated robot, and the point cloud and the gripper meshes don't align. So this happens because the robot's internal kinematic model does not agree with the real world or its true physical self. So we need to update the robot model or the robot URDF. So on the right, you can see that you can see the result of a calibration system where the point cloud blends in very nicely with the gripper mesh. So advantages of a Fetch calibration system is fast. It takes less than 3 minutes for calibration to happen. It gives you repeatable results, and it's robust. So Fetch calibration is the configuration for our robot calibration package. It's essentially a bunch of YAML files. And robot calibration package is where our robot generic calibration code lives. Robot calibration happens in 2 phases, the capture phase and the calibration phase. In the capture phase, we capture data about calibration targets, and this indirectly gives us information about the kinematics and the sensors, which are present in the robot. And the calibration phase is optimizing the parameters of the system by essentially minimizing the error between the sensor and the kinematic alignment. A good calibrated robot knows exactly where its body parts are, while if you have a bad calibration, the robot might think that its head's detached from itself, or your arm's twisted, or something weird like that. So calibration for us at Fetch is very important because we produce a number of fetches, and the technicians assembling these robots aligns the joints by eye with a few degrees of accuracy, and calibration is needed to correct this error and to understand the true model of the robot. So usually when the technicians assemble robots, they need calibration jigs or correction jigs and stuff like that to align the joints properly. But our calibration system's so awesome that technicians can just align the joints by eye, and after calibration, we'll know the true model of the robot. Okay, so the capture phase. During the capture phase, the robot moves through a series of predefined poses, which have been selected as a representative sample of the positions where calibration is required to be valid. We need to make sure that these samples or these positions have enough information about all the joints that need to be calibrated. So we need to take the data of the target from different angles and at different distances. We use MoveIt to move the robot to the captured poses. And the calibration phase always records the position of each and every joint in the robot at each of these capture poses. We have 3 finders that are available in the package: the LED finder, the checkerboard finder, and the ground plane finder. Also, additional finders can be added very easily. Okay, so the LED finder essentially looks for the 4 calibration LEDs which are present in the gripper, and these LEDs are blinked in a pattern, and the depth sensor is then able to find these LEDs it uses a simple thresholding algorithm which looks for these transitions. We use this finder because it makes the robot self-sufficient and very easy to calibrate. We can also attach a checkerboard to the gripper for calibration. We use the standard OpenCV checkerboard detector to detect the position of each of the corner points that are present in the checkerboard, and the position of each of these points is directly measurable by the camera. All right, so the ground plane finder was originally added to reduce the distortion in the ground, or to basically flatten the ground plane. So the head camera is used to find planes which are close in location and in orientation to the true ground plane. And this can improve calibration, especially at longer ranges, since the arm can give us data or information only up to a distance of 1 meter. Right, the optimization phase. So during the optimization phase, we reproject the expected position of the calibration target through each of these kinematic chains and sensors. And the difference between these reprojections or these measurements forms a residual over which optimization is then performed. So our system uses the series optimizer to solve the reprojection error minimization problem. So series is based on creating a problem with one or more free parameters and one or more error blocks. So the optimizer will then attempt to find the optimal values for each of the joints of the robot, or each of the free parameters, based on minimizing the residuals from each of the error blocks. So free parameters are fairly straightforward. They typically consist of joint offsets, link offsets, camera intrinsics and extrinsics, while error blocks use data from one or more sensors and reproject them to a common frame. And then they compute the residual between these reprojections. Right. So the LED detector essentially looks for the 4 LEDs that are present in the gripper, and once the camera finds them, the points are then reprojected from the camera frame to the base link frame. And we know where these LEDs are mounted on the gripper, so the position of these LEDs is reprojected to the virtual arm sensor, again to the base link. So and the difference between these two reprojections then forms the residual over which optimization is then performed. So it's the same thing for the checkerboard calibration, except that the number of points increases. The ground plane method is slightly different, and because we have no way of finding a full 3D estimate of the individual points by just looking at the ground plane, we only compare the pose of the points against plane z equal to 0 in the robot baselink frame. So then these error blocks are fed into series to get the offsets. So our calibration system is designed to work with ROS, or the robot operating system. So therefore, once we have estimated our offsets, we update our robot URDF or the robot model. So this slide basically shows the variances for each of the joints, and this is calculated over 25 different calibrations. And as you can see that the variances are really low, around the order of 10 to the power minus 6 for most of these joints. So we get repeatable results from our calibration system. So this video compares the robot and point cloud alignment before and after calibration. On the left, it's pretty clear that the point cloud and the end effector positions don't match, and you can see that a gap exists between the point cloud and the gripper fingers. While on the right, we can see that the sensor or the point cloud is very well aligned with the gripper mesh. All right, so calibrating the freight. So calibrating the fetch was cool, but we make another robot at Fetch Robotics called the freight. Freight is a mobile base which does not have an arm, but it does have a time-of-flight camera that's mounted at an angle. So the same ground plane finder, which was discussed earlier, is used to calibrate the pitch of this camera. So the camera looks for points that are on the ground, and then these points are reprojected again, reprojected from the camera frame to the baselink frame. And once we know the points that are on the ground, so the height's basically 0. Height 0 in the baselink frame, so we basically minimize the difference between these two readings. And our face calibrate in less than 10 seconds. Right, so some final remarks. Fetch calibration is awesome. It's a robot generic calibration system. It's fast and it's repeatable. Our fetch robots are now able to pick and squish rubber duckies, which is awesome. And also you can find our open source code available for the fetch calibration package under Fetch ROS, which is the first link. And the robot calibration is available at github.com/MikeFerguson/robot calibration. And further documentation about how to use our calibration packages is available at docs.fetchrobotics.com. Oops. Now we shall open for questions.
Do you do any calibration of your wheel diameters?
Calibration off?
Wheel diameters of your
No,
base?
not right now. Okay. We're just doing the joints and the sensors, or the head camera.
Great presentation. How did you determine the predefined trajectories to run through for calibration?
So initially we had collected 100 samples, which were basically random, but then we wanted to, and it took about 10 minutes for a calibration to happen, so we decided to, then we wanted to make it faster, so we reduced the number of trajectories, which was again completely random, but then we got to a point that we realized that once your data needs to be rich enough for calibration to happen, so those poses were manually selected by us, making sure that the robot moves through maximum rotations at each of these calibration poses, so you actually get enough information.
Are there any other questions?
It seems that you are trying to overcome the noise of your perception systems and your effector systems. I want to know that some type of the noise is because of the environmental factor, for example, lights or other things, which will be changed during the time. How you will to adapt to that type of the noise?
So you're talking about the exposure and stuff that happens when there's light?
Yes, for example, you see here, you're in this condition, your distance is something like that, but when the environment is changed, the light is changed, maybe it's different.
Okay, so that was one thing that it was a problem that we encountered. So one thing that we could do for the ASUS Prime Sense or the Karman that we're using is that we could switch off auto exposure, and also we take 10 consecutive snaps for the LED blinking. So basically, and then it's a simple thresholding algorithm which kind of just it gets rid of the exposure problems that we have.
Okay.
Because it's 10 snaps and then thresholding stuff.
Yes, thank you.
Very quick question. Have you applied this calibration method in order to get a more accurate gazebo model of your robot?
So that's what this does. It updates. So that's what this does. It updates the internal robot URDF. So and then you can use that to update because the gazebo model essentially uses the URDF, right? So you would get. Okay. It's updating the gazebo model or the internal robot, or what the robot actually is, basically. Updating the internal robot model.
Thanks to your talk. If I want to use fetch calibration to our own robot, which part do I need to modify? Or it just
it was the last. So you need to look at fetch calibration package, which is essentially the configuration so you'll know how to give the free parameters and all the stuff that you need to define there. And while the main code is present in the robot calibration package, which was link number 2 in my talk.
Okay.
So you need both those two calibration packages together.
Thank you.
Thank you.